Now, using this diagram of ripple tank experiment, we are to find the values of optical path difference for constructive interference and for destructive interference. So first we will see the meaning of optical path difference. त्याच्या नावावरून आपल्याला समजेल मग इट इज द डिफरन्स बिटवीन द पाथ अँड व्हॉट इज मीन बाय पाथ. पाथ मीन्स इट इज द डिस्टन्स कवर्ड बाय द ऑब्झर्वर, बाय द वेव, by the particle, by the body. In this case, we are considering the wave zone. So the meaning of path difference is like this. The difference between the distances covered by two waves arriving at a given point. The differences between the distances covered by the two waves arriving at a point gives optical path difference at that point. That as the position of point of crossing changes, path difference will also change. Like this. So now we know the meaning of path difference. It is the difference between the distances covered by the two waves arriving at a given point gives the optical path difference at that point. The path difference depends upon the position of the point of crossing. So we are considering two simple examples. Example number 1. So S1 and S2 are the two sources at distances 16 and 20 cm from the point P. The waves from S1 and S2 cross each other at point P. So path difference at point P is equal to S2P minus S1P. This distance is 20 cm. Larger distance, this is smaller distance. So 20 minus 16, that is equal to 4 cm. Now in the second example, we are considering this situation. Suppose this is the point Q. So this is one wave, this is another wave like this. So the wave is shown like this. The wave is shown like this. Suppose the two waves have same. So this is 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, 5 lambda by 2. So this distance is 5 lambda by 2. This is 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, 6 lambda. This distance is 6 lambda by 2. So path difference at point Q is equal to AQ is more than BQ, and this AQ is equal to 6 lambda by 2. Sorry, 6 lambda. This is 5 lambda. So path difference is equal to lambda. This one cycle complete means lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, 6 lambda, and 6 and half. Sorry, 6 and half means this is equal to 13 lambda by 2 and this is 11 lambda by 2. So please make the correction. इकडे ह्या 5.5 and half वेव्ह देते 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda and half lambda. So this is the 13 lambda by 2 minus 11 lambda by 2, so that is equal to 2 lambda by 2, that is equal to lambda. So part difference between the two waves crossing each other at point Q is equal to lambda. So either you can find the part difference in terms of millimeter, centimeter, meter. If we know the wavelength, we can find the distance in terms of lambda, or directly we can measure the distance lambda. So to measure the distance lambda in our figure, we know this scale. R1 is equal to lambda by 2, R2 is equal to lambda, R3 is equal to 3 lambda by 2, etc. आता हा कन्सेप्ट यूज करून आपल्याला इथे कन्स्ट्रक्टिव्ह इंटरफेरेन्सचे जे पॉईंट्स आहेत हॉलो सर्कलने मार्क केलेले, तर तिथे आपल्याला पार्ट डिफरन्सचे व्हॅल्यू कॅल्क्युलेट करायचे आहे. लाईक दिस. तर अगोदर आपण आता इथून सुरू करू. कन्स्ट्रक्टिव्ह इंटरफेरेन्सचे पॉईंट ऑफ व्ह्यू आपण कन्सिडर करतो. ऑप्टिकल पाथ डिफरन्स for constructive interference. This is case number E. So we will consider this point. Let this point is denoted by P1. So part difference at point P1 is equal to, now one wave will come from A, so AP1, second wave will come from B source, BP1. So this is the distance covered by the first wave. So this P1 point lies on 1, 2, 3, 4, 5 on fifth circle. So AP1 is equal to R5, BP1 is also R5. So by this scale, R5 is equal to 5 lambda by 2. So distance covered by the first wave is 5 lambda by 2. 5 lambda by 2. So this is equal to 0. So part difference at point P is 0. आता ह्याच लाईनवर समजा आपण इथे P2 पॉईंट घेतला. याच लाईनवर घेतला P2. So this is case number 1. Second case. So the second point we will consider this P2. Already we know the part difference at point P1. We have calculated in the case number 1. So one wave arises from A at point P1. Second wave arises from B at point P1. So AP1 is the distance covered by the first wave. BP1 is the distance covered by the second wave. P1 point lies on the fifth circle. 1, 2, 3, 4, 5. And therefore this AP1 and BP1 both are radii of the fifth circle. And we know this scale R5 is equal to 5 times R1, so 5 times lambda by 2. पहिल्या सर्कलची रेडियस आपण लॅम्बडा बाय 2 घेतली, सेकंड त्याच्या डबल, ट्रिपल, क्वाड्रुपल याप्रमाणे. सो 5 लॅम्बडा बाय 2 minus 5 lambda by 2 is equal to 0. So P1 point has optical part difference 0. Now we have to find the part difference at point P2. So part difference at point P2 is like this. Part difference at point P2 is equal to, now this P2 point is at distance A, P2 from source A, B, P2 from source B. So P2 point lies on the first, second, third circle. So this is equal to R3 minus R3. So that is equal to 3 lambda by 2 minus 3 lambda by 2 is equal to 0. म्हणजे इथे पण पार्ट डिफरन्स 0. म्हणजे आता जनरलायझेशन आपण काय करू शकतो, पार्ट डिफरन्स ॲट पॉइंट this is 0, this is 0, this is 0, this is 0, because they are equidistant from the point E, like this, and therefore we can generalize. So on this line, optical part difference is 0 for any point. आणि ही लाईन आपण एक्सटेंड केली आणि इथे एखादा पॉईंट घेतला, इथे एखादा पॉईंट घेतला, तरी ऑप्टिकल पार्ट डिफरन्सची व्हॅल्यू 0 देणार. सो फॉर constructive interference one value that is possible is optical part difference is equal to 0. आता हे नेक्स्ट लाईन घेऊ आपण constructive interference. मग या लाईनवर जर आपण पॉईंट जर घेतला आपण याला आता P घेऊ. सो केस नंबर 3 part difference at P3 is equal to. Now P3 point is at longer distance from B. So I will subtract BP3. I will subtract AP3 from BP3. आता BP3 distance बघा. B point पासून first, second, third, fourth, fifth circle वर आहे. So this is BP3 is equal to R5 and AP3 is equal to R3. So this is equal to 5 lambda by 2 minus 3 lambda by 2. इथे पार्ट डिफरन्स लॅम्बडा आला 0 ने आला. या लाईनवरच्या सर्व पॉईंटसाठी पार्ट डिफरन्स 0 आहे. इथे लॅम्बडा आला. इथे लॅम्बडा असेल तर इथे पण लॅम्बडा येईल, इथे पण लॅम्बडा येईल. So all the points on this line will have optical part difference is equal to lambda. By symmetry, इथे पण part difference zero देईल. Optical part difference is equal to lambda. You can check. आज जसा P3 पॉइंट घेतला तसा इथे आपण हा P3 पॉइंट जर घेतला तर EP3 minus BP3 सारखे. So optical part difference is 0. Optical part difference is lambda. Optical part difference is 2 lambda. या लाईनवरचा ऑप्टिकल पार्ट डिफरन्स आपल्याला 2 लॅम्बडा मिळेल. चेक करून बघा. समजा आपण हा P4 पॉइंट कन्सिडर केला. वन मोर केस. केस नंबर 4. पार्ट डिफरन्स ॲट पॉइंट P4. इथे आपण P4 घेतला. So BP4 is longer distance. AP4 is a shorter distance. So BP4 means 1, 2, 3, 4, 5 circle. So this is R5 and this is R1. So 5 lambda by 2 minus 1 lambda by 2. So that is equal to 4 lambda by 2. That is equal to 2 lambda. The आपण लिहिलेली व्हॅल्यू करेक्ट आहे. So on this line the optical part difference OPD is equal to 2 lambda. So part difference is 0. Part difference is lambda lambda. Part difference is 2 lambda 2 lambda. Now we can generalize. आपण जर सर्कलच्या रेडियस कमी केले आणि A and B मधलं डिस्टन्स चेंज केलं तर ऑप्टिकल पार्ट डिफरन्स आपल्याला अजून काही व्हॅल्यू मिळू शकतात. सो फॉर कन्स्ट्रक्टिव्ह इंटरफरन्स ऑप्टिकल पार्ट डिफरन्स इज आयदर 0 और लॅम्बडा और 2 लॅम्बडा 3 लॅम्बडा 4 लॅम्बडा 5 लॅम्बडा L लॅम्बडा. हे आपल्याला जनरलायझेशन आता करता येईल. सो फॉर constructive interference optical path difference is equal to 0 lambda 2 lambda 3 lambda 4 lambda 5 lambda etc. In general it is equal to n lambda where n is equal to 0, 1, 2, 3, 4, 5 integer, or optical part difference is equal to n lambda or 2 times n lambda by 2. So this 2n is always even number. So this is equal to even multiple of. We are expressing the value in terms of lambda by 2. Even multiple of half a wavelength. So this optical part difference condition is given like this. This 2n is always even number. If n is like this, then what is 2n? 2n is equal to 0, 2, 4, 6, 8, 10, etc. So n is a positive integer number and 2n is a even number 0, 2, 4, 6, 8, etc. So this is the condition. Condition of optical part difference for constructive interference is optical part difference is equal to integer multiple of wavelength lambda or even multiple of lambda by 2. दोघी पद्धतीने आपण कंडिशन लिहू शकतो. So this is first part. Now let us see the condition of optical part difference for So this is the very important use of this figure. We can calculate the values of optical part difference for the points of constructive interference and for the points of destructive interference, and here we are using this scale. R1 is minimum distance lambda by 2 पहिल्या सर्कलची रेडियस आहे. R2 is equal to 2 times R1 means 2 times lambda by 2, 3 times lambda by 2, 4 times lambda by 2, etc. So using this scale, now we have to find the part difference at the various points. So here now we will consider the point Q1. I will show point of destructive interference. The point is say Q1. So part difference at point Q1 is equal to BQ1 longer distance minus AQ1 check the figure. We have taken so here we have considered the point Q1. So we have to find the part difference at point Q1. So it is equal to BQ1 minus AQ1. Q1 point is at longer distance from B and it is at shorter distance from A, therefore BQ1 minus AQ1. So BQ1 is the radius of the 1, 2, 3, 4, 5, fifth circle R5, and AQ1 is the radius of the fourth circle. So the part difference at point Q1 is given by BQ1 minus AQ1, that is equal to R5 minus R4. And that is equal to 5 lambda by 2 minus 4 lambda by 2, that is equal to lambda by 2. So for destructive interference, the first value of optical part difference is lambda by 2, like this. Now we will consider the next point. आता ह्या लाईनवर आपण कुठे जरी पॉईंट घेतला तरी पार्ट डिफरन्सची व्हॅल्यू लॅम्बडा बाय 2 जाणार आहे. वेदर दिस इज ऑल द पॉईंट्स विल हॅव सेम व्हॅल्यू ऑफ पार्ट डिफरन्स. So all the points on this line has part difference 0, part difference lambda. So on this line the part difference will be between 0 and lambda, and it is lambda by 2. So I will add in our figure. By symmetry we can get the same value here also. So part difference is between 0 and lambda, so this is equal to lambda by 2. By symmetry, part difference on this line is also lambda by 2. Now, this part difference is lambda, this is 2 lambda. So, on this line, the optical part difference will be equal to 3 lambda by 2. By symmetry, optical part difference is equal to 3 lambda by 2. तर हा part difference आपल्याला व्हेरीफाय करायचा आहे. त्यासाठी आता इथे मी पॉईंट कन्सिडर करू. कन्सिडर द पॉईंट Q. So, Q2 point is at longer distance from this A. So part difference at point Q2 is equal to AQ2 minus BQ2, and that is equal to, check करा. So Q2 point is taken here. So it is a longer distance from A. So AQ2 is equal to radius of the fifth circle R5, and BQ2 is equal to radius of the second circle. So this part difference at point Q is equal to AQ2 minus AQ1, and it is equal to R5 minus R2. R5 AQ2 is equal to R5, radius of the fifth circle minus R2, so that is equal to 5 lambda by 2 minus 2 lambda by 2, that is equal to 3 lambda by 2. So the value we have written is correct. So part difference is lambda by 2, 3 lambda by 2, lambda by 2, 3 lambda by 2, like this. जर आपण सर्कल फिगरमध्ये चेंज केला सर्कलच्या रेडियसमध्ये A आणि B पॉईंटमधल्या सेपरेशनमध्ये, आपल्याला अजून काय व्हॅल्यू मिळू शकतात. सो इन जनरल पार्ट डिफरन्स हॅज व्हॅल्यू λ/2, 3 λ/2, 5 λ/2, 7 λ/2, 9 λ/2, 11 λ/2, all odd multiple 1, 3, 5, 7, 9, 11. So you can generalize this condition. So for destructive interference, optical part difference is equal to λ/2, 3 λ/2, 5 λ/2, 7 λ/2, 9 λ/2, 11 λ/2, etc. So this is equal to odd multiple of λ/2, and odd multiple is written as 2n minus 1 into λ/2, where n is equal to 1, 0 नाही घेतला इथे पण 2, 3, 4, 5, etc. So optical part difference has a condition like this. Odd multiple of λ/2, इथे इवन मल्टिपल आहे, इथे ऑड मल्टिपल आलं, म्हणजे लक्षात ठेवायला पण सोपं झालं. सो फॉर कन्स्ट्रक्टिव्ह इंटरफेरेन्स द ऑप्टिकल पार्ट डिफरन्स इज इवन मल्टिपल ऑफ λ/2, दिस इज ऑड मल्टिपल ऑफ λ/2, ऑड मल्टिपल ऑफ λ/2. आता फेज डिफरन्सने पण व्हॅल्यू आपल्याला देता येईल. सो वन सायकल correspond to distance λ correspond to phase difference 2 pi radian, and therefore λ/2 corresponds to pi radian. इथे λ/2 घ्यायचे आपण पाय जर टाकलं तर phase difference ची व्हॅल्यू पाय, 3 pi, 180 degree, 540 degree, etc. So the same conditions are given by phase difference is equal to pi radian, 3 pi radian, 5 pi radian, 7 pi radian, 9 pi radian, etc. So this is equal to odd multiple of pi radian. λ/2 correspond to pi radian. तसं इथे पण आपल्याला विचारलं, इवन मल्टिपल ऑफ λ/2 means even multiple of this pi. So these conditions are 0, λ means 2 pi, 4 pi, 6 pi, 8 pi, like this. याच्यामधले व्हॅल्यू 0 ने 2 pi च्या मध्ये इकडे pi द्यायला 2 pi and 4 pi च्या मध्ये. So these are the value of phase difference for constructive interference, phase difference for destructive interference, part difference for constructive interference, part difference for destructive interference. तर मागे जे आपण डिस्टिंग्विशचं टेबल तयार केलेलं आहे कन्स्ट्रक्टिव्ह डिस्ट्रक्टिव्ह इंटरफेरेन्सचं, तर त्याच्यामध्ये या व्हॅल्यूज आपल्याला ॲड करता येतील मागच्या केसमध्ये. सो वी नो द व्हॅल्यूज ऑफ फेज डिफरन्स ॲज वेल ॲज द पार्ट डिफरन्स लाईक दिस. So now from this figure we have derived the condition of optical part difference for constructive and destructive interference. So in the table of distinguishing point between constructive and destructive interference, we can add the remaining 2 points. Point number 6 is about the optical part difference, and point number 7 will be for phase difference. So just now we have found this value, only you have to add in that table. So please add in that table. Optical part difference at the point of crossing is OPD is equal to 0, lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, etc. So this is equal to n lambda, or integral multiple of wavelength lambda, n is equal to 0, 1, 2, 3, 4, 5, etc. OPD is equal to 2n into lambda by 2. So n is like this, therefore 2n is equal to 0, 2, 4, 6, 8, 10, etc. So OPD is equal to even multiple of half wavelength. Now on this side, optical part difference at the point of crossing is OPD is equal to, the first value is lambda by 2, 3 lambda by 2, 5 lambda by 2, 7 lambda by 2, 9 lambda by 2, 11 lambda by 2. So optical part difference is equal to odd multiple of lambda by 2, and odd number is given by 2n minus 1 into lambda by 2, where n is equal to 1, 2, 3, 4, 5. n की वैल्यू 0 पासून सुरू होत नाही, like this. So part difference is given like this, or this is also given by n minus half lambda. For this value, n start from 1, that value is this. So these are the values of part differences, optical part differences, like this. Now next point we will consider the phase difference. Phase difference delta phi. This part difference is also denoted by delta lambda or delta x. Phase difference delta phi between two light waves, at the point of crossing is delta phi is equal to 0, lambda corresponds to 2 pi radian, 4 pi radian, 6 pi radian, 8 pi radian, 10 pi radian, etc. So that is equal to even multiple of pi radian, even multiple of pi radian. It is even multiple of lambda by 2 is lambda by 2 correspond to pi radian, like this. Now on this side, phase difference delta phi between the two articles at the point of crossing is delta phi is equal to lambda by 2 means pi radian, 3 pi radian, 5 pi radian, 7 pi radian, 9 pi radian, 11 pi radian. So delta phi is equal to odd multiple of pi radian. Even multiple of pi radian, odd multiple of pi radian. So these are the values of part difference and phase difference, like this. So we will require these conditions for solving MCQ problem also. So this is the distinguishing point between the constructive and destructive interference. Already the first 5 points we have seen. For constructive interference, the light waves arrive at a point in the same phase. For destructive interference, out of phase. So for constructive interference, same phase crossing will give the addition of the dispersion, maximum amplitude of the resultant wave, maximum intensity of light at the point of crossing. Point appears bright. तर ते पॉईंट ऑलरेडी आपण बघितलेले आहेत, फर्स्ट 5 पॉईंट. These are the new points that is added like this. Now in the initial part of this chapter, we have seen the meaning of secondary sources, secondary waves in Huygens principle, and we have taken this example. Suppose this is a primary source, so it produces the primary source, point source kept in homogeneous air medium, so it will produce the waves, spherical wavefront. So this is the circle of crust, circle of trough, circle of crust, circle of trough, circle of crust, circle of trough, etc. Now, if a screen is kept like this, so it is having two holes, S1 and another hole, S2. So when the primary waves from S reach the S1, it becomes secondary source. When the primary waves from S reach the point S2, it will become secondary source and it will produce the secondary waves. So secondary waves are moving like this. Circle of crust, etc. like this. So these are primary waves, these are secondary waves. So S1 and S2 are secondary waves. S is a primary source, S1 and S2, S1 and S2 are secondary sources. So these two secondary sources receive the light waves from the same origin source. So such sources are called as coherent sources. So S1 and S2 are coherent sources. Also S1 and S2 are called coherent sources. Because both sources will produce the light waves of same frequency, and the phase difference between them is, in our figure, it is 0 or it is constant. So d distance is SS1, d distance is SS2. So SS1 is equal to SS2 is equal to 1, 2, 3, 4, 4 circle R4 minus R4 is equal to 0. So part difference is equal to 0. Phase difference is equal to 0 and it is constant. So in this case, the secondary sources S1 and S2 are called coherent sources. So they are secondary sources, but they are obtained from one and the same original source. They are producing the light waves of the same frequency and phase difference between them is 0, कॉमन. आता जर आपण हा स्क्रीन जर टिल्ट केला तर फेज डिफरन्स 0 ने आला. So depending upon the position of S1, S2, the phase difference between S1 and S2 remains constant. Depending on positions of S1 and S2, phase difference changes, but remains constant for given position of positions of S1 and S2. Phase difference remains constant, and therefore S1 and S2 are called as the coherent sources. The coherent sources at definition मध्ये आपल्याला हे 3 पॉइंट घ्यायचे. They produce the light waves of the same frequency. The phase difference remains constant independent of time t. केव्हाही जर आपण या दोघांमधला phase difference घेतला तर तो 0 असणार आहे. So such sources are called as the coherent sources. So the definition of the coherent sources include the 3 points, and which are like this. Now we will give the definition of coherent sources. The sources of light which emits waves of same frequency and having constant phase difference independent of time. The sources of light which emit the waves of same frequency and having constant phase difference independent of time are called coherent sources. This is the definition. What is the property? Characteristics of coherent sources. Phase difference delta phi between the waves from two coherent sources. Is always remaining constant. And 0 is less than equal to delta phi less than or equal to 2 pi radian, like this. Phase difference की value किती बनू शकते? It depends upon the distance between S1 and S2, like this. So this is the property of the coherent sources. The phase difference is remaining constant. So to produce the coherent sources, method number 1 is this. It is shown already in this figure. A screen is having two holes, S1 and S2 pinhole, and this screen is kept in front of S so that distance SS1 is equal to distance SS2. So when the distances SS1 and SS2 are equal, then the phase difference between the waves producing from S1 and S2 will have phase difference 0, and this phase difference remain constant. Therefore, S1 and S2 acts as the coherent sources. Second method is by using the biprism. So the name itself suggests that it is a combination of two prisms, therefore it is called as a biprism. So in this case, using the biprism, we get the two virtual images, one formed by one half prism, other by other half prism. So these two virtual images act as the coherent sources. So in Fresnel biprism action, we will see this use of biprism to produce the coherent sources in detail. The third method is by using the Lloyd's mirror. This method is also given in detail in our syllabus. So these three methods we have to use. So in this case, S1 and S2 are secondary sources, S is the primary source. The waves going from S to S1, S to S2 are primary waves, and waves coming out from S1 and S2 are secondary waves, like this. So S1 and S2 produces the secondary waves. They are having same frequency. They are having constant phase difference 0, and the phase difference remain constant independent of time t. Therefore, Therefore, S1 and S2 behaves as the coherent sources, like this. So, this method is used in Young's double slit experiment. It is called as a double slit experiment because there are two slits. इथे आपण होल म्हटलेलं आहे, तिथे आपण स्लीट यूज करावं, नॅरो रेक्टँग्युलर स्लीट यूज केले जातात लक्षात. सो दिस इज अबाउट द कोहेरेंट सोर्सेस. कोहेरेंट सोर्सेस आर नेसेसरी producing the stationary interference pattern. Necessity for coherent sources. In one sentence, you can give to produce TD or stationary interference, we require the coherent sources. So for steady interference pattern, there are some other conditions also, coherent sources, monochromatic sources, etc. So coherent and monochromatic, these are two important conditions. We already know the meaning of monochromatic. The two sources will produce the light waves of one and only one wavelength, like this. Okay, we will stop here. Next time we will see the Young's double slit experiment to produce the stationary interference pattern, like this.